Okay, good evening. Okay, let's get started. This is the second lecture with relevance to the vibrations, isolations, and control. Okay. In this lecture, we will have more examples, in-class examples for you. The major objective for using these examples is to let you know how to do the calculations. Because I don't know how many of you understand better about in the previous lectures and whether you already learned it before. So that's I need to move slowly in order to deliver all information and knowledge to you. Because this is one of the topics in your final examination. So that's why I need to explain more details in this one. Okay. Okay, now what is vibrations? You know that I explained many times that vibration, you may regard this is repeated motions or periodic motions. Okay, similar to this one, we have a plate. Okay, a plate like this one, a horizontal plate. We put it on. We connect this vibration, vibrating plates to our shaker. Okay, we use the amplifiers to control the signals to generate a single pure tone effects to this square plates. Okay, can you answer me how we can visualize the vibrations effects of this one? How to visualize this one? To visualize the vibrating effects of this plate, we can put a group of sand particles, lightweight particles, on this plate, on the surface of the plates. Let's take a look what happens. Frequency. So when we increase the frequency effects, you can see that the patterns could be different. Okay, we can generate different patterns on this plate. This is the vibrations voltage on this plate. Okay, when we adjust the frequency values. When we further increase the frequency values, you can see that different patterns could be generated. This is the real situation of this plate under vibrations effect. When you refer to this one, this patterns, we can guess, we can assume all these sand particles on the positions. We call this is the nodal positions, where the sand particles could not move. Okay, without movement, without vibrations. Only those areas in dark color, they are under vibrations. They are under vibrations. So you can change the frequency values to what you like. Okay, you can find many videos from the YouTube about this one. Okay, let's go back to our lecture. Before go to the last system, okay, first and then the vibration system, I want to take a few minutes to go through the first two in such a way that you can refresh your memories about how to do the computations. For the first type of and then the vibration system, we just care about two components, M and K. M is the mass and K is the stiffness. Stiffness is the material properties. The larger the values of the stiffness, the harder to do deformations. Because when you refer to the units of this value, okay, when you refer to the units of K, the units is in terms of Newton per meter. Okay, so that's the larger the value, it means that more force to be added on the system in such a way that you can move its distance. Okay, reference to the units. The second one is that we introduce one more component here, is the damper, and C is the damping coefficients. What is the values? Why we just consider M and K in the first system? Because in the first system, based on these two parameters, we are able to find out the natural frequency of the system. In the second part, although we introduce one more term, we still use M and K to find out the natural frequency of the system. Okay, and the third one, for the third one, we consider this is a sinusoidal force. Okay, please pay attention. This is not a constant force. If you just consider a single force F here, this is not correct. The calculations procedures are different. In here, we assume that this is a sinusoidal force. Okay, and omega with a bar here. This one. This is not the natural frequency. This is the external frequency. Okay, the external force with a frequency acting on this system. Okay, omega with a bar. Okay, now in the previous lectures, I already explained the difference between the free vibration, forced vibration, then and undamped system to you. When you refer to this one, free vibration, it means that we do not have an external force acting on the system. Okay, similar to a pendulum system like this one. We just apply excites the system, and then we do not apply external force to it. Similar to this system. Okay, originally we do not have any vibrating, we do not have any damping system. Okay, we just consider the spring constant and mass, so that you consider the amplitude, it could not decay against the time effects. Okay, you can see that this is a simple pendulum system. Okay, you could move up and down without dissipating energy. Okay, now if we introduce an damping effect, let's say we reset the system and then we put 0.2 in this one and start again. As time goes on, you can see that the amplitude could decay. Okay, this is the damping system. And if we introduce an external force, let's say it is equals to 1. Okay, you may refer to the blue line here. Okay, blue line represents the time history response on this mass. But because here the external frequency is less than the natural frequency, so that no resonance occurs. If I change it to 3, okay, the external frequency is 3 radians per second. It is very closer to the natural frequency here. You can see that the blue line resonance occurs. Okay, like this one. This is not the effects we want to achieve. Okay, because you could amplify the vibrations effect, and also it could increase the noise effects. Okay, now let's go back to this one. This is the first equations I introduced to you. Okay, in your final examination, these equations could not be given, so that these simple equations, you know how to make use of it. And based on K value and M value, we are able to find out the natural frequency. Here, F with a subscript N here, you represent the natural frequency. Okay, if I request you to find the angular frequency, actually we are talking about this equation, this one, omega N. Okay, omega N and Fn, the units are different. Please pay attention to that, because the only difference is this one, 2 pi here, 2 pi. And if we only if we only know the diffraction effect or the spin, okay, we can record these equations to find out the natural frequency. In this equation, please bear in mind that sigma is in terms of millimeter, not meter, okay? So that's why if you substitute the diffraction values into this equation, you can find out Fn, okay? If we don't know the values K or M, okay? And this one, strength connections, there are two forms. The first one is in parallel. In parallel, you just need to add all the strength stiffness together. Okay, no matter they are equal or not, you just add up together to find out the equivalent stiffness. If they are connected in series, you may refer to these equations. They are different. I have two examples in your lecture notes to show the difference between them. The first one is exercise 2A. In this example, they are both strengths are connected in parallels. You can see that the final results in terms of the angular frequency is 14.14 radian per second. And the second one, for the second questions, if even the stiffness, the values, they are the same, but if the connections configurations they are different, you can see that the results is totally different. So please pay attention on this one, the connections. And then I already showed this ones to you. And okay, now we go to the free and damped vibrations. Now we have one more parameters here. You see damping constant, and the unit is Newton per meter per second this time. Okay, now you may skip this one. I just want to show you that how we can, because for those vibrating systems, we could use second order differential equations to represent the equations of motions. I don't want to make too difficult, and I don't want to present too much mathematics to you. Okay, this is just for your reference, how we can find out the critical damping effects. I just want to share with you that here, we have three cases, over damping, critical damping, and under damping effects. Okay, in our study, we just focus on the last one. The reasons why I explained it before is that for the first two types, over damping and critical damping, low oscillations occur, like this one, like this one. Okay, we use zeta. Zeta is damping ratios to represent, to identify which categories we are going to consider, whether this is over damping effects, critical damping effects, or under damping effects. When you refer to the over damping case, critical damping case, you can see that no oscillations occur. Okay, when we release the system, okay, the system will go to zero without any oscillations about its equilibrium positions. Only the last one, when zeta is less than 1, when the damping ratio is less than 1. In between 0 and 1, okay? This is what we call the under damping case. In this case, oscillations occur. Okay, it means that vibrations about its equilibrium positions could occur. Okay, when you refer to this one, okay, this case zeta, we define this as the actual damping values derived by critical damping effects. Okay, critical damping, we can calculate critical damping based on two values, K and M. Okay, you may use the first equation or the second equation. It's up to you. And how about C? The values of C is given in questions. Okay, this is the actual value, so that you compare this value with respect to the critical value. If it is less than 1, we can classify this as the under damping case. It means that oscillations occur. If it is equal to 1 or larger than 1, no oscillations occur. Okay, how about if damping is equal to 0? Okay, if zeta is equal to 0, it means that C must be equal to 0. Okay, if C is equal to 0, that means low damping effect. Okay, low damping effect. So any problem about these two parameters, zeta and the critical damping constants? Okay, we set this critical damping constant is we need to have a standard line to compare the damping effects. Okay, we have 3 different cases. So now we move to this one. This is more complicated. If we want to consider a damping effects, this is the final result. This is what we call the displacement solution. Displacement solution. A is amplitude. Where is amplitude? Okay, you can see that amplitude is here. This is A. Okay, this is A. But you may have a question that as time goes on, the amplitudes could decay, correct? There is a term here. This is called this is what we call the exponential function. With the presence of these exponential functions, as time goes on, amplitudes could decay. When you can imagine that when time is equal to 0, what does it mean? If you substitute 0 into this term, it becomes the exponential function is power to 0. What's the values of this one? It is equal to 1. So that at time is equal to 0, the amplitude is equal to A. But as time goes on, the amplitudes could decay because of the presence of this one. Okay, any problem? And please bear in mind that this is potential functions. The power is in terms of zeta. Zeta is damping ratio. Omega n, what is omega n? Natural frequency. And T is time. Okay. We still have another term, is the harmonic term. In terms of the harmonic term, what is omega d? Okay, let me explain to you later on. T is time. Okay, T is time. And how about phi here? Phi is the phase angle. Okay, you may regard this one A. A can be calculated by using this equation. Okay, it seems that it is so complicated. You don't worry about it. All of these equations could be given. You just need to plug in all the correspondence values into the equations. You are able to find out the overall displacement solutions, so that you don't need to memorize all these equations A, phi. You just need to know how to calculate omega n. Okay, omega n and zeta. Zeta is so simple. It's the comparisons between the actual damping values and the critical damping value. Okay, and how about A is given here? Let me explain to you that what is V naught. What is V naught? V naught is the velocity. It means that like this one. When time is equal to 0, what is the velocity at time is equal to 0? We write it as V naught. Okay, I explain again. When time is equal to 0, that means this is the initial condition. Initial conditions. What is the velocity? This is the velocity. Okay. We have 3 components. One is displacement. The second one is velocity, and the third one is acceleration. V naught here, it means that at time t is equal to 0, the values of v, we call this is V naught. Okay. And how about S naught here? S naught is the displacement. At time is equal to t. At time is equal to 0. This is S naught. V naught and S naught. Okay. Both conditions should be given, otherwise you cannot find out the value. Okay, so when we refer to this one, V naught is the initial displacement value, and zeta is the damping coefficient, damping ratio. Omega n is natural frequency. S naught is here, displacement at time is equal to 0. Okay, any problem? And how about omega d? Omega d is given here. It is relevant to omega n and the damping effects. If the damping ratio is equal to 0, that means omega d is exactly equal to omega n. Okay. Okay, any problem about the first equation? How to find out A? How to find out the values A? So based on these equations, what can you observe? You can observe that the amplitude, the initial amplitude, it depends on all these parameters. And the other one is that what is phi? Phi is given here. Okay, the same. It's not omega d, v naught, theta, and omega n. If we know all these parameters, we can substitute to get the values of phi. Okay, so when the values A is known and the values phi is known, we can go back to this equation and substitute to find out the displacement solution. Any problem about this one? So that please bear in mind that you just need to know how to calculate omega n and this one, theta. Omega d is given here. It is relevant to omega n. If theta is equal to 0, what does it mean? Omega d is equal to omega n. Okay. Okay. Even it appears that this is so complicated. We don't have complicated mathematics here. We just substitute all the solutions back to these equations. We are able to find the displacement solution. Okay, now what I want to share with you using this figure. In this figure, we have three curves. The first one, the red one is 0% dampen. It means that no decays in terms of amplitude. If there is 10% dampen, the blue line, you can see that as time goes on, the amplitude could decay. If we further increase it to 20% dampen, it can go further. Okay, it can decay further. So this is the this is relevant to this equation. Okay, this is relevant to this equation. Okay, now here this is the first in-class exercise for you. We have three parameters, M, K, and C here. You have to determine all the following items here. Okay, please take about 5 minutes to find out the results, and then we compare the answers together. Okay, now we just have these three values. How you can find out the results? Can you find out the answer? Okay, please keep in mind these three values. M is equal to 1, K is 2, and C is 0.5. Okay, now for the first one is the angular frequency. Okay, so that's it's so simple. The equation is equal to K divided by M. Okay, so 2 divided by 1 and 10 to the square root. This is the angular frequency. How about the natural frequency? The natural frequency, there is a difference in 2 pi, so that it becomes 0.225 hertz. How about the natural periods? Natural periods is the reciprocal of the frequency, so it is equal to 1 divided by 0.225. This is the natural periods. Okay, 4.44 seconds. Okay, and how about the critical damping constant? In terms of the critical damping constants, we recall this standard equation, okay? It is reference to m and omega n. Because m is equal to 1 and omega n is equal to what? This one, 1.414. So that's the critical damping constant is 2.828. Okay, this one. Okay, now the final one is the damping ratio. In terms of the damping ratio, we compare the actual value. The actual value in this case is 0.5, and the critical one is 2.8. So the damping ratio is equal to 0.18. Okay, based on this value, can you tell me about what types of damping effects? Under damping effects. Okay, this one. This is the under damping effects because the ratio is less than 1. Okay. So now you know what is the value we call this is actual damping and what is the values we call this is critical damping. Okay. Actual damping is given here in the questions, 0.5. Any problem about this all these solutions in this question? Okay, now let's take a look on this exercise number 6. Let's go through this one together. Under the influence of ground vibrations, a person's leg has a measured natural frequency of around 20 Hz. This is the first one. 20 Hz is the natural frequency. When it is in rigid position in the longitudinal directions along the length of room with a damping ratio 0.224. Okay, 0.224. Please, this is the damping ratio and this is the natural frequency. There are two small problems here. The first one is to calculate the response of the tip of the leg boom to an initial velocity V0 is equal to 0.6 meter per second and 0 initial displacements. Okay, what is the meaning of this one? This is what we call the initial velocity. V0 is equal to 0.6 meter per second. It means that the velocity at time t is equal to 0. The value is equal to 0.6 meter per second. Okay, this is what we call V0. And how about this one? Zero displacement, initial displacement. It means that S0 is equal to 0. Okay, why we need to have these two conditions? Because the first question is to request you to find out the response of the tube. What equations we need to use? This one. This is the displacement solution. Okay, you cannot just record these equations to answer question A. Okay, you need to find out each parameter, each one. Okay, let me remove this one. This is the first question. For the second question is that what is the maximum acceleration experienced by the unit assuming no damping? Okay, the second one is different from the first one because from the first one we need to consider the damping effects. We have a damping effects, but the second one we need to assume there is no damping effects and to find out the maximum acceleration. Okay, let us move on to the first one. A. According to the questions, we just have these three parameters. Theta is equal to 0.224, V0 is equal to 0.6 meter per second, and S0 is equal to 0. Okay, all of them are given. Okay, now what is the natural frequency? The natural frequency now because theta is less than 1, so that this must be an underdamping case. Okay, this one is less than 1. And how about the natural frequency? Omega n is equal to 2 pi fn. Okay, now as given in the questions, this is 20 Hz, so that's why omega n here, the angular frequency is equal to 125.66 radian per second. Why I need to change the form, the frequency in terms of radian per second? Why we don't just use f? Because when you go back to this one, there is a term here, omega n. So that's why we need to convert it back in terms of omega n rather than we use fn. Okay. Okay, what is the damped frequency? What is damped frequency? What is damped frequency here? Damped frequency is omega d. Omega d, okay? Omega d, there is an equation here. Omega d is equal to omega n times the square root 1 minus theta square. So based on that, we got the answer is 122.47 radian per second. Okay, so far on this page, we just need to calculate the damped frequency. Okay, all others they are given. Okay, now we go to find out the response. The response M to A. M to A here, we record this equation is correct. Okay, we substitute one by one to this equation. V0 is given 0.6. Theta is equal to 0.224. Omega n is the natural frequency, so that you may substitute 125.6 to this value. And S0, what is S0? Initial displacement condition is equal to 0. And how about another one, another term here? S0 is still, omega d is 122.47, and S0 is still 0. So that according to the upper part, this one, we can cross out this one because this is equal to 0. This is also equal to 0. We just have the upper part, 0.6. Lower part, omega d only. So you can calculate the value is about 0.005 meters. Okay, in this case, this is the equations to find out the M to A. Okay, no any difficulties. We just plug in the values into the equations. Any problem here? Okay, now we go to this one, the phase angle. Still remember that we have another equation to find out the phase angle phi. Okay, how about the equations for phi? The equation is this one. Because S0 is equal to 0, so the upper parts, no matter how large is omega d, it must be equal to 0. For the lower parts, V0, we do not need to calculate this one because 0 derived by anything, it is also equal to 0. Okay, so the phase angle here is equal to 0. Any problem? Because the upper part is equal to 0, so that no matter how large or how small the lower part, it is also equal to 0. Arctangent 0 is equal to 0. Okay, once we got the values amplitude A and the phase angle, we can find out the response. The response is like this. Now, A, we got it is 0.005, okay? And how about theta? Theta is 0.224. Omega n is 125.66. And T, we do not need to calculate T. T is a time history response, okay? You can substitute any response times to this one. And how about omega D? Omega D is 122.47 times time. And find the values find here is equal to 0. The only one you need to wrap up all these calculations is that when you use 0.224 times 125.6, you can get 28.15. This is the final form. This is the final form, okay? So when you can write down this one, this is the final response. Time is a variable only. In this case, you can change it by yourself. Originally we say that it's not it is equal to what? 0, correct? Okay, when t is equal to 0, what does it mean? The psi function here it becomes 0, so that all of them it becomes 0. Okay. Okay, this is just for part A only. Okay, to find out the response. How about the second question? The second question is to find out the maximum accelerations that can be experienced by the leg assuming no damping. How to find out maximum acceleration? What is the meaning of maximum acceleration? Okay, you may go back to this one. This figure shows a simple harmonic motion. Okay, this is the displacement amplitude, this is the velocity amplitude, and this is the acceleration amplitude. What is the maximum acceleration? The maximum acceleration is omega square s. Okay, this one. If you consider that this is a simple harmonic motion, the displacement is expressed in terms of this one. When you differentiate this term once, you can get this one. Okay. We call this one is the velocity amplitude or the maximum velocity. Why we call this one? Because the function here, cosine function, the maximum value is 1 and minus 1. So that the maximum value should be omega times s. For the acceleration, what is the maximum value? Omega square s. Okay. So the second part in question number 6 is to find out the maximum accelerations. I recall the equations here. The maximum acceleration is equal to the angular frequency squared times a. A, what's the value of a? This is a, correct? But we need to recalculate the values of a again. Why? Because in part A here, the damping ratio is 0.224, but in part B we assume low damping effect. So this value it becomes 0. Okay, in part number 1, in part A, the damping ratio it is equal to 0.224, but in part B, this term should be equal to 0. Okay, as stated in the questions, we do not consider damping effects. Damping effects can be ignored, so it is equal to 0. Okay, you can see that when this part it becomes 0, you just have V naught here. How about the low part? Because theta is equal to 0, so that it becomes omega n. So you can find out that A, we can express it in terms of V naught divided by omega n, correct? And you can put this term, back to this one. When you put this term back to this one, it becomes V naught is 0.6 is given, and omega n you can cancel out with respect to the first one. So that this is the final result. Because this is the acceleration, so the unit is meter per second square. Okay, let's take a break first. Please take a look on this exercise. If you have any problems about how to find out the solutions, you may ask me. Okay, let's come back to the second part. I think that you do not need to worry about that the difficulties levels in these subjects, although there are many calculations in these subjects. As I told you before in the first lecture, this is not just descriptive subjects. This is calculation-based subjects. Okay, and I remember that when I first year come to Poly to teach these subjects, at that time I show all the differential equations and no any response from the students because no one can answer my questions. So that I refine and polish all the lecture logs year by year, and then to simplify the versions. And hopefully it can help you understand all this one. Okay. Okay, now go to the final one, the forced standard vibrations. Okay, don't worry about this differential equation. These equations, I want to let you know how we can construct this system. In this system, okay, even you don't know this equation, it doesn't matter, but you can identify three parameters, M, C, and K, correct? Okay, the first one, it refers to mass, C is damping constant, and K is stiffness. When you refers to what's the values, S is displacements. S dot, it refers to velocity, and S dot, it refers to acceleration, okay? You may regard like to this form. Okay, you may regard S dot it is A, this is V, and this is S. Okay, what's MA? MA is a force, correct? According to the Newton's second law, MA is a force. So that we just put the left-hand side and the right-hand side, they are equal to each other. And how about on the right-hand side here? As I told you before, the last type system, vibration system, we consider that this is a sinusoidal force function, And omega with a bar here, it refers to the external frequency, This is given, So when we refer to this equation, we need to take care of two more terms. The first one is F, and the second one is omega, correct? Okay, now, I already state here is that this is a damping ratio to compare the actual damping with respect to the critical damping, correct? And omega, sometimes when you refer to my lecture logs, if I just write it as omega, it refers to the natural frequency, okay? Natural frequency. Omega here is equals to omega n, okay? Because sometimes I skip the subscript n here. It is equal to k over m, correct? Okay, now, this is the external frequency, like this one. This is the external frequency, and force is a constant value. Sometimes you may further rewrite the form here, F naught is equal to F divided by M, so that if you use the whole equations divided by M, you can go to the second one. You can go to this one. I could not teach you how to solve this one, okay? I just want to let you know what we need to do. For this one, when you consider forced standard vibrations equations, when you refer to some reference books, they could let you know that, or applied mechanics, there are some sections about this one to find out the overall solutions. There are two parts. The first one is the complementary solutions, and the second one is what we call the particular solutions. Okay. For the first part, what is this one? What is this one? This is similar to this one. Okay. Oh, sorry. Why we have two parts? Because to solve this problem mathematically, we need to consider the procedures like this. We first consider that there is no the forces term on the right hand side. We got the first solution. If we consider there is a term on the right hand side, we need to consider the particular solutions. Okay, now for the particular solutions, I already stated here. Okay, and these equations could be given. So again, you just need to substitute all the correspondence parameters into this equation. You can find out the steady state response. Okay, let me explain to you how to find the steady state response under these effects. Now, for the first time, we call this is the static displacement. The upper part is F naught. What is F naught? It's the force per unit mass, F divided by M. And how about the lower parts? Angular frequency, the natural frequency, correct? Okay, so any problem about the first part? Okay, remember F naught it is equal to F divided by M, or you may call this one is the force per unit mass. For the second part, this is what we call the dynamic application factor. When we refer to this one, there are two parameters. Zeta, you know what is zeta? Okay, damping ratio. How about beta? Beta is the frequency ratio. Please bear in mind that the ratio must be equal to the external frequency derived by the natural frequency. Okay, you cannot reverse the order. If you reverse it, you cannot get the correct answer. It must be equal to the external one derived by the natural frequency, like this one. Okay, this is what we call the frequency ratio. Okay, not difficult. We just need to consider these two parameters, zeta and beta. And the third one is the harmonic term, because you know that we apply a sinusoidal force to this system. Okay, the motion is like this one, up and down. Okay, so that's what is this one? Omega with a bar, external frequency, and phi is given here. When you take a look on the equations for the values phase angle, you can see that we still need to consider zeta and beta only. Okay, no other parameters. Okay, I could not derive how we can get this ones to you. Okay, but I just want to let you know to find out the steady state response for the forced and damped vibration system, we could use this equation, and this equation is similar to the response for the damping case. It is given. Okay, but you need to know how to find beta, zeta, F naught, and omega n. That's it. Okay. When you refer to this steady state response, what does it mean? It means that like this one. When we set it to 2, okay, and start the simulations, you can take a look on the blue line. Blue line represents the displacement response of this mass. Okay, the response you can see that this is not purely periodic. Okay, the amplitudes could be changed as time goes on. This amplitude, the blue one, we can make use of this equation to find out the blue one. Okay. Okay, again, I want to remind you, beta is the frequency ratio. It must be equal to the external one derived by the natural frequency. When you use the angular frequency omega, this one should be equal to omega. When you use the natural frequency f in terms of hertz, both of them should be expressed in terms of hertz. Okay. Okay, this one is the maximum steady state amplitude. Okay, when you compare this equation and this equation, what is the difference? What is the difference between these two equations? Okay, this page and this page. Can you tell me what is the difference between these two equations? Okay, in this equation, we do not consider the last terms, correct? Why? Okay, this is the maximum steady state amplitude, okay? And this is steady state response. If we just consider the steady state, why we do not need to consider the harmonic term? Because the psi function here, the value psi is, the maximum value is equal to 1 and minus 1. Okay, so that's, if we want to find out the maximum value, we can assume the last term is equal to 1. Okay, so we just take care of the first two terms only, the static displacement and the dynamic amplification factor. If we are going to find out the maximum steady state response, this is a common effect why we consider the maximum. The first case is under the maximum static response, correct? Okay, if we can control the maximum steady state, it means that if it is safe, we can control well the system. So that's why we always consider the worst case is at the maximum steady state response. Okay. Okay, now we go to this one. As I told you, we just consider the first two terms to find out the maximum steady state. We do not need to consider the psi functions, the psi harmonic term in this equation because the maximum value is equal to 1. Okay, let's go back to this one. Why I need to derive this one? F naught, originally I say this one is the force per unit mass. And what is the omega square? Omega is the natural frequency, correct? So that we can further rearrange like this one, F divided by K. Okay, it depends, it's up to you. You may make use of this equation or this equation. I just want to let you know that both of them, they are equivalent. The only difference is that F naught is equal to F divided by M. And beta must be equal to the external frequency divided by the natural frequency. Okay, any problem? In the last system, in the last case, force and tandem vibrations, we just need to consider this equation, this one. This is the most important equation. Okay, now let's take a look on some practical cases. The first one is the unbalanced rotating vibrations. What does it mean? Normally, if you consider that this is a rotating fan or motor system, okay, why it could create the structural bond noise effect? We may simplify the scenario like this. Okay, we have the mass system. Okay, this is the total mass supported by structure, and there is a rotating part. We can use this as the rotating part. The rotating mass is we can regard this as a small letter m. What is E here? E, we call this one is the eccentricity. Eccentricity. Okay, you may regard this as the length from the center to this mass. Okay, any problem? And the rotational speed, it is relevant to the omega bar times t. Okay. Why in this slide I just picked up some important points here. Well, we consider that S is the displacement. When it is in rotation, when this mass is in rotations, it creates a vertical motions up and down, up and down. Okay, because of the rotations of this small mass, it creates an unbalanced force. Okay. Regarding this system, the displacement of small mass, we can make use of this simple relationship. And the external force, how to find the external force? It is we can consider the external force is relevant to the small mass times the eccentricity times the angular frequency, the external frequency square. Okay, this is the rotating frequency. Rotating frequency is here. Why we need to find out this one, external force? This is the force to create force and effects to this system. In this equation, if we want to find the maximum steady state response, we need to find the mass. And here, F is equal to m times E times omega square. Any problem? Okay, I explain again. For a forcing system, we need to make use of these equations to find the maximum steady state response. Okay, when it refers to the maximum steady amplitude here, it is reference to F, K, beta, and theta, 4 parameters only in these equations. For the force, when you consider some general machineries, such as the rotating machines, what is the external force created from these machines to the structure? The external force is relevant to this one. Okay, you may ask what is M? M is here, the small mass, the rotating mass. What is E? E is the direct separation distance from the center to this mass. Okay, E, the unit is in terms of meter, and omega square is the external frequency. Okay, let me show you an example here. We have a 30 kilogram electric motor shown here. It is supported by 4 springs, and each of them is 200 Newton per meter. Okay, each one the stiffness is 200 Newton per meter. If the rotor is unbalanced such that its effect is equivalent to a 4 kilogram mass located 60 millimeter from the axis of rotation. What does it mean here? The scenario, it is likely that 4 kilogram mass it is equal to m, the small letter m here. Okay, this is 4 kilogram, similar to this mass. Okay, according to the questions, it tells us that we can regard the system like a rotating system, and the small values m mass, we can assume it is equal to 4 kilogram. And how about the eccentricity? It's 60 millimeter. That means the value E here is equal to 60 millimeter. But in calculations, please change it back in terms of meter. Okay, we do not use millimeters for calculations. Any problem? So based on the questions, m is given, E is also given. And how about we need to determine the maximum static amplitude of vibrations when the rotor is turning 10 radians per second. What is this one? 10 radians per second. This is omega with a bar. Okay, this is the external frequency. And the damping ratio theta is equal to 0.15. Theta is equal to 0.15. It means that this is under damping case. Okay, less than 1. How about this one? There are 2 mass values here. One is 4 kilogram mass. Okay, 4 kilogram mass is this one, the small letter m. How about this one? 30 kilogram. This is the big letter m. Okay. You may regard that we have a large mass. Inside the mass, we have a small mass in rotations. Because of that mass, it creates an unbalanced force to drive the motions of the whole system. Okay, any problems about this one? We match the values for each parameter. Okay, now let's go to the calculations part. Okay, the first one is to find the maximum steady state amplitude. What does it mean? It means that we need to consider this equation, correct? Okay, the pivotic force that can result the motors to vibrate is the centrifugal force due to the unbalanced rotor. First of all, to find out the external force, we need to consider these equations. Given from this one, given that m is equal to 4 kilogram, E is equal to 0.06 meters. Okay, this is please pay attention. This is equal to 60 millimeter, but in calculations, I told you that we need to change it back in terms of meter, otherwise you cannot get the results. And what's the external frequency? External frequency is 10 radian per second. Okay, this is the angular frequency, so that you can say that the unit is in terms of radian per second. And force, the unit of force is Newton. The unit of force is Newton. Based on these three parameters, we got the answer is 24 newtons. Any problem? Okay, this is one of the parameters to find out the maximum static response. The second one is the stiffness. The total stiffness is 4 times 200. Why? We have 4 springs, correct? They're connected in parallel, so that the equivalent stiffness of the whole system is equal to 800 Newton per meter. What else we need to find out? The natural frequency. How to find the natural frequency? Is K derived by mass. What's the mass in this case? What's the total mass? 30. 30 is the total mass of the whole system, correct? Not 4 kilogram. 4 kilogram is the rotating mass, not the total mass. Okay, mass, the total mass is 30, and the total stiffness, please pay attention here, is equal to 800, okay? So that's why the natural frequency of the system is 5.164. How about the frequency ratio? What's the frequency ratio? The frequency ratio is this one, correct? 10 derived by the natural frequency. Okay, whether this is a Western case or not, this is not a Western case because the external frequency is not exactly equal to the natural frequency. Okay, if it is equal to 1, resonance occurs. If it is not equal to 1, it means that no resonance occurs. Okay. Okay, now we got the values, the external force, the stiffness, the natural, the frequency ratio, and one more parameters. What is the last one? Damping ratio, correct? How about the damping ratio? What is the values of damping ratio? The damping ratio is given 0.15. So now we finish all calculations. We just need to plug into these equations. Okay, substitute into these equations. F is 24, K is equal to 800, beta is 1.936, and theta is 0.15. The maximum static response is 0.0107 meters. Okay, in this case, what does it mean for this one? Is that when we have springs to support these rotating machines, the maximum displacement the machines can achieve is just 0.01 meters. That means this one, okay, this one. The maximum vertical displacement it can achieve under the operations of this one is 0.01 meters. We are now looking for this one, okay? Okay, is it more clear about how to make use of this equation? Okay, any problem? Okay, another example. Now, your turn. Okay, please take about 5 minutes to go through this one, how to find out the results. In this example, you need to find out the, there is a word missing here. It should be maximum amplitude. Here, highlighted in red color here. Okay, you need to find the maximum amplitude under the conditions here, and what is the frequency of the 4 vibrations required to cause resonance? There are 2 questions. The first one is to find out the maximum amplitude under the steady state response, and the second one is to find out the resonance frequency. Okay, please take about 5 minutes to go through this one. Sigma here is the displacement. Okay, displacement. And there is a hint here. Sigma is equal to A sine omega t. Okay, omega with a bar here. This one is the external frequency. You may compare exercise number 7 and exercise number 8 to see how to find out the results. Can you find out the answers? Okay, this exercise is similar to what we did in exercise number 7. Let me explain to you. Now, we have an instrument like this one, and this instrument is originally attached to this platform. With the provisions of this platform, there are 4 springs, identical springs supporting this structure. Okay, and what is the vibrations created from this system? The floor. Okay, the floor is subjected to a vertical displacement. Okay, sigma is equal to 10 psi ht millimeter, where t is in terms of seconds. You have to determine the maximum amplitude of steady state response. Now, there is a hint here. Sigma is expressed in terms of a sine omega t. Okay, when you compare this equation and this equation, what can you find out? What is the values of omega bar? Is equal to 8 radian per second, correct? And how about now, because we want to find out the maximum amplitude, so that's one of the problem. We need to find out f, k, theta, and beta, correct? Do we know f and k? Is it given in the question? Okay, go back to the first principle. We just have the displacements. What's the relationship between f and k? F is proportional to k times sigma. Okay. When you consider this one, you may consider that f is equal to k times s. S is the displacement, k is the stiffness. So based on that, the natural frequency of the system here is equal to 800 times 4. Why we need to times 4? Because there are 4 springs here, correct? And the mass, what is the mass in this case? The mass is 20 kilogram. The natural frequency, it becomes 12.65 radian per second. How about the amplitude of steady state response? Please pay attention here. The first term is f times k, because now we just know that the displacement, sigma. So we just plug in sigma into this equation. Okay, sigma here, it is equal to f of k. Why we do not need to consider this one? Why we do not need to consider this one, psi omega t? Because we are now going to find the maximum response, maximum case. So the maximum displacement in this case is 10, correct? Okay, when we put sigma is equal to f divided by k, the upper part is 10. How about beta? Beta is to compare the external frequency and the natural frequency. The external frequency is equal to 8, correct? Here, when you compare the value here and this equation, omega with a bar must be equal to 8. And theta, what is the value of theta? 0. It is it. We don't need to consider this one. So in this case, the value it becomes 16.67 millimeter. Okay, this is the maximum response. The critical point is the critical point here in this question is that you need to understand the relationship between the displacement and force and stiffness. Okay, any problem? Okay, let us move on. And we still have the second question in this problem is that what is the Westerns frequency? Westerns frequency is exactly equal to the natural frequency. In this case, it is equal to 12.65 radian per second. So that's why this is the answer. We do not need to calculate again. Okay, in this statement, Westerns will occur when the amplitude of vibrations caused by the forward displacement approaches infinity. Why it goes to infinity? Because in this case, we do not consider the damping effects. If there is no damping effect under Westerns effect, it could go to infinity. This is a very ideal case. In realities, we cannot achieve this case. Okay. Any problem about this solution? Now, why I need to let you know this one? Because we have many practical applications to consider the force standard effects. Let's say you consider this as a stream under the dynamic effects. There is a force that can be transmitted through the structure. Okay, transmissibility is the ratios of the amplitude of the force transmitted to the supporting structure. That means this is the ratio between Ft and F. Okay, this is the transmissions ratio. Okay, for the transmissibility, how to calculate the transmissibility? This is the ratio between Ft and F. What is Ft? Ft is here, the amount of force. This one, the amount of force that can be transmitted through the connected structure. And how about F? F is the original external force. Okay, so we compare these two parameters. When you compare these two parameters, we find out that the ratio can be expressed into this equation. This equation, when you take a look on this equation, it is very similar to this equation, correct? But be careful. This one is to use to find out the maximum static response, and the transmissibility is this equation. Okay, and this equation should be given. Okay, you do not need to memorize these equations. When you refer to these equations, we just have two parameters. One is theta and one is beta. There is a statement here without damping effects. It becomes this one. It means that when theta is equal to 0, these equations can go to this one. But when you do any calculations, even in your individual assignments or in final examinations, you need to start consideration for the first equation, not the second one. Okay, if you consider this one, you always assume that the damping effect is equal to 0. Okay, I want to let you know that how to read this figure. When you look at this figure, the y-axis is the transmissibility. We want to have a high values of transmissibility or low values of transmissibility. Low value, okay? Low value, what does it mean? It means that the values of Ft must be equals to low value, okay? That means the amount of force we can control within small amounts, okay? When you refer to this one, y-axis is the transmissibility. This is 1. What is the meaning of 1? When T is equal to 1, it means that F is equal to Ft. That means when you apply 10 newtons to the system, 10 Newton force can be transmitted to the structure. Okay, that is not a good approach. We want to minimize this force, so that we always want to achieve the system lower than 1, lower than 1. So when you take a look on this one, this is the regional isolations. We always want to achieve this region, not about 1. If we want to achieve this one, this is what we call the regional amplification. Okay, I explain again. This is the transmissibility. We want to design a system to go to this region, regional isolation. We don't want to achieve the system to the regional amplifications. Okay, if under these regions, it means that resonance occurs. Okay, you could amplify the sound effects, vibrations effects. Okay, now how about the s-axis? The s-axis is frequency ratio. This is beta, okay? And there is on the right-hand side, this is the theta. So that this figure connects 3 parameters: the transmissibility, the frequency ratio, and the damping ratio. Okay, when the frequency ratio is equal to 1, okay, that means the external frequency is equal to the natural frequency. Under this case, beta is equal to 1, correct? When beta is equal to 1, what does it mean? It means that resonance occur, this part. And this is the regional amplification. How we can achieve this system? How we can we go to the regional isolation? Not at this one. We need to design a system. The ratio must be equal to √2 or larger than √2. In that case, we can go to the regional isolation. Okay, again, let us remove all this one. We have the transmissibility, frequency ratio, and damping ratio. First of all, we just talk about the transmissibility and the frequency ratio. If the frequency ratio is equal to 1, it must be going to the resonance region. Okay, this is resonance. You can see that. In this case, let's say we can achieve this one is 10. It means that when T is equal to 10, F and Ft, the ratio between is 1 to 10, correct? Okay, when you refer to this one, when T is equal to 10, the ratio between Ft and F must be equal to 10 to 1, correct? It means that when you apply 1 Newton to the system, the transmitted force becomes 10 Newtons. Okay, this is resonance case. How to design an appropriate system? We need to make sure that the system, the frequency ratio must be equal to √2. At √2, the transmissibility is equal to 1. More than √2, it is less than 1 when you refer to the figure here. Okay, can you observe this one? When the value is larger than √2, we can go to the regional isolation. Okay, this is what we want to achieve. And the damping effects, when you refer to this one, when you increase the damping ratio, you can observe the different characteristics of the system. Okay, I say here is that transmissibility is equal to Ft divided by F. When T is equal to 1, it means that Ft is exactly equal to F. This is not the ideal case. When T is larger than 1, amplifications occurs. When T is less than 1, it means that we can achieve the reductions of vibrations effects. It means that we can achieve vibration isolation. Okay, in terms of the isolation's efficiency, we can write it into this form. T here is the transmissibility. It means that the higher the transmissibility, the lower the isolation's efficiency. And the lowest the transmissibility, the highest the isolation efficiency. And the vibrations reductions, we can make use of these equations to express the results. Remember that when we apply the log functions here, the units is still in terms of dB, okay? Although we are talking about the vibrations reductions here, because we apply the logarithm functions here, so that's why the units is still in terms of dB. Any problem? Okay, now this is what I mentioned before. According to the statements here, we want to go to the regions of isolations, not the regions of amplifications. What I want to share with you is this one. This is the regional isolation, and this is the regional amplification. Sorry. Okay, now let's go to this page first. To design a system, okay? We want to achieve this region, as I told you before. And the critical point is here, √2, correct? At √2, no matter what values of the damping ratio, it should be equal to 1. This is the minimum one. If we want to achieve an isolation design, it must be more than √2, okay, larger than √2. What does it mean, √2? √2 is the frequency ratio, correct? What is frequency ratio? Okay, frequency ratio is equal to the external force, external frequency derived by the natural frequency. Okay, any problem? Okay, in terms of the external frequency, no matter this is the rotational frequency or what else, we cannot control it. It depends on the system. We can control the natural frequency. Okay, if we have a machine, the mass, we cannot change the values of mass. Okay, you cannot change the value of mass. What parameters we can change? The stiffness. It depends on what types of springs you can install to support that system. Okay, that means if you change the values of K, we can change the values of Fn. Correct? If we can change the values of frequency Fn here, we can change the frequency ratio in such a way that we have to make sure that it must be larger than √2. Do you know what I want to share with you? When you refer to this figure, again, I repeat one more time. We want to achieve the frequency ratio larger than √2. Okay. For in terms of beta, it is equal to the external frequency derived by the natural frequency. We cannot change the external frequency. How about the natural frequency? The natural frequency, it depends on these two parameters. If we consider a machine, we want to control the natural frequency. The only parameters we can adjust is the values of K. Okay, you can increase the stiffness or decrease the stiffness depending on what types of springs you are going to install to support the system. Okay, the criterion is that you need to make sure that the frequency ratio must be larger than √2. In this case, we can go to the regional isolation. Okay, this is the critical point. Okay, we may stop here in this lecture so that after this lecture you can go back to digest all the information here. And now we take a 5 minutes break and then we go back to our tutorial. Okay, let's go to our tutorial sessions. In this tutorial, number 6, we still have two questions for you. Both of them are relevant to Rayleigh noise assessments. For the first one, you have to find out that the angle of view and the reflections of opposite facades in each case. And the second one, now, in the previous tutorial, we just considered one single variable. Now we consider two variables in parallel together and find out the overall noise level to these reception points. Please go through again. This one, this stage predictions methods according to the your lecture logs. Okay, and take about 30 minutes to go through all of them, and I will explain the answers to you later on. Okay. So, following the stage here, please think about how to handle the case for two variables in parallel together. Okay, this is a real situation. You may refer to tutorial 5 solutions and see how to solve the problem for question number 2. Okay, let's discuss together. Okay, question number 1. We need to refer to this figure. Okay, when we look at this figure, how many sections we can derive? Okay, how many? We can derive when you refer to this figure. There is a refractive barrier here along the sections in between this railway and this building, so that we may derive into two segments. The first segment is 38 degrees with the presence of this refractive barrier, and the other one is this one. Okay, this is 142 degrees. Okay, two segments. When we derive into two segments, the first one is to find out the angle of view. For this one, we may derive into two segments. The first one is 38 degrees, and the second one is 142 degrees. For segment 1, if theta is 38 degrees, alpha is 19 degrees. Still remember how to find out alpha? Alpha is to draw a parallel line and then measures from this parallel line to the bisection line of theta. Okay, so that if theta is 38 degrees, the bisection line of theta is 19 degrees. And the segment 2 is when theta is 142 degrees, alpha is 71 degrees. Okay, any problem? Now, for the first one, when you refer to the figures provided in your lecture logs, when we consider 38 degrees and 90 degrees, the first correction is minus 12.5 dBA. For the second one, 142 degrees and alpha is 71 degrees. 72 is minus 0.28 degrees dBA. Any problem? Okay, for the reflections from opposite facades, we assume that all of them, in terms of the refractive barrier, the first building, second building, and the third buildings, they could contribute reflections to these reception points. We assume all of them can contribute. Okay, now when you refer to the segment 1, this is segment 1. Okay, the noise effect is generated along this rail track because with the presence of this refractive barrier, all the reflections effects could be blocked by this refractive barrier at segment 1 only. For segment 2, 142 degrees, the opposite facade, because this is a refractive barrier, so that it may contribute reflections to the reception points. So we need to consider theta 1. All of these buildings, all of these 3 buildings, they are hard surfaces. Okay, so that's why we need to cater for all these 4 angles. So in terms of segment 1, the corrections is equal to 0 dBA. And for segment 2, there is standard equations in your lecture logs. You just add up all of the angles together, and the total angle is 142 degrees. So that's why the correction factor is 0.74 dBA. You may refer to this one. Okay, this equation. In this equation, theta pi, the upper part theta pi is that you just add all of them together, and theta at the lower part is the overall value. Okay, any problem about question number 1? Okay, question number 2. For question number 2, now we need to consider a two-track system. This is a two-track railway where 2 types of trains could operate. The first one, track number 1 is CWR types on borders, and track number 2 is a joint track. Track number 1, there is the types of vehicles is H identical passenger coaches, and the type is MKI type with 120 km per hour. And the second one is on track number 2 is H identical passenger coaches, but the type it becomes British Rail MK3, but they travel at 130 km per hour. The numbers of trains, they are different. For track number 1 is 192 during the daytime, and at night is 18. For track number 2, they are 285 and 30. The reception points to the track number 1 is 100 meters away from the reception points. From the second one is 103 meters. Now we need to find out the total noise effects. How to do this one? First of all, there is only one segment. We do not need to derive into different segments in this case because there are no any barriers or obstacles between the tracks and also the reception points. And then you can list out all the information given in the question, such as the angle of wheel, the type forms, train types, the speed, and the numbers of trains in during the daytime and at nights. And the reception points, in the previous tutorial, I already explained to you that the effective source is at the wellhead. Okay, so that the height above the wellhead is 3.3 meters. Because now the reception point here is 4 meters above ground. The wellhead, we assume, is equal to 0.7 meters. So that's why the difference between the wellhead and the reception points is 3.3 meters. Okay, we have 2 separation distance. D1 is 100 meters and D2 is 103.5 meters. Okay, and this should be 103. Okay, this should be 103. And the average height of publication should be 0.7 plus 3.3 over 2. Okay, now the stage number 2 is that we need to find out the reference noise level. We have to consider a total number of 3 conditions. Okay, you have to derive into 2 parts for track number 1 and track number 2 because we now just have 1 segment, but we have 2 types. Okay, track number 1 and track number 2. Based on different train speed, from chart A1.1 we got for train number 1, track number 1 is 72.8. For track number 2 is 73.5. You can follow one by one. You have to consider individually for each type first. Okay, each track. Okay, you cannot mess up both tracks together. And then you follow one by one to find out that the reference noise level for track contributed from track number 1 is 96.6 and track number 2 is 91. The major difference is that the speed is different and the track form is different, so that you have to find out the correspondence values. At stage number 3, the publications. One is the first one is distance corrections. For the first one is 100 meters. The second track is 103 meters. The second conditions is air absorption corrections, ground corrections, correction for forest type, screening correction, and angle of view. We construct another table to consider one by one. Okay, it is not difficult to consider separately for track number 1 and track number 2. I want to highlight this one, borderless corrections. For borderless corrections, track number 1 is 0 dB. Why? when you go back to your lecture notes, in terms of the Border's corrections, these conditions, we just consider this case when we have a parallel tracks, two tracks, okay? And the condition is that track number 1 should be a Border's type. If track number 1 is not a Border's type, we do not need to apply any corrections for this case. Okay, so if track number 1 is a Border's type, so that's when you consider track number 2, you need to make minus 1.5 dBA for the corrections factor, because I explained to you during the lecture that if this is a Border's type, it can have to absorb small amounts of sound effects. So that's why we made corrections factor here at minus 1.5. But for track number 1, no any correction. Okay, no any correction. So when we go back to this one, you can see that none of the corrections factor should be applied on track number 1, but minus 1.5 dBA should be applied for track number 2 in this case. Okay, I repeat again, if track number 1 is non-Border's type, track number 2, we do not need to apply minus 1.5. The only condition is that track number 1 must be a Border's type. Okay, so that's because there is no screening structure, so both of the tracks, the corrections factors are equal to 0. And for no matter for track number 1 and track number 2, the angle of wheels, they are the same. Theta is equal to 180 degrees and alpha is 90 degrees. Okay. Now, facade corrections, a correction is required as the reception point is 1 meter away from building facade, so that we use 2.5 dBA as the reference value. 2.5 is stated in the documents. And the opposite facade, we assume that there are no buildings or other rigid surfaces on the opposite side, so that's why it is equal to 0. Okay, so that's in this case, at this stage, both of them, the reflection corrections factor is 2.5. Now, stage number 5 is to convert sound exposure level to LAEQ value. Okay, you just add up all of them one by one. Okay, this is for track number 1, this is for track number 2. Track number 1 in this case is 91.2, and for track number 2 is 83.8. We still highlight this one is to apply. We have an equations. Still remember that this one. Okay, we need to make use of these two equations to find out the LAEQ value. So you can get for during the daytime and nighttime, each track contributes. Let's say for track number 1 at night is 60.5, during the daytime is 65.9. It depends on the numbers of vehicles passing through these reception points. Okay, now we go to the last stage. For the last stage is to calculate the overall value. Now the overall value should be contributed by both tracks. Okay, track number 1 and track number 2. So during the daytime and at night, how to find out 61.6? Okay, this one and this one. You may consider at night these two values. How to calculate this one? Still remember that we have an equation like this. To calculate the overall value, okay, this is at night. Contributed for track number 1 is 60.5, track number 2 is 55.6. The total value is equal to 10 knot. Okay, this is the total value. This is the total value. You can check it by yourself. By using this equation, you can get this value. This is at night. During the daytime, you can make use these two values, and then use the same equation. You can find out the result. Okay, so that's if we consider two parallel tracks, the first step you have to consider one by one, and finally at the final stage you combine all of them together. You can make use of this equation or chart number 9. Okay, where is chart number 9? This is chart number 9. Okay, if we have two sources, we want to find out the overall level. You can find out the difference between them. With the presence of the difference, you can locate the correction factor and add it to the higher value. Okay, so there are two alternative approaches. The first one is to use the direct calculations, and the second one is to make use of these charts. Okay, any problem? So this is the final answer for the total level received by the reception points at night and during the daytime. Okay, I will upload all these ones to you on next Monday for your revisions. Okay, thank you. One more point I want to remind you, on next Friday, we have the second lab sessions. Please follow your assigned schedules to attend the lab session and tutorial. Thank you.